Very good evening to friends here, and good morning to our speaker, Tiffany Santos. Good afternoon to friends in Europe. It's really my great pleasure to welcome you all to this very special lecture, 86th lecture of the webinar series on spin tonics. We call it W2S, which has started almost 22 months back, and it's going very well just because speakers like Tiffany, Mtjs, and others who are on board today, who have been very kind accepting my invitation and coming forward to give lectures to this community. And during pandemic, it was really nice. Now, of course, we are starting again offline activities, but still, I think this online seminar is appreciated. People cannot travel and they will greatly benefit interacting with experts. So on behalf of my team, co-convener Braj, other team members, Puspendra, Shakti, Ajay, Swayam, and others, I welcome you all again to this 86th webinar of the webinar series on spin tonics. So Tiffany, I think, is very well known in our spin tonics community. She actually does not need a formal introduction, but there may be some of our young students, for their benefit, I would like to say a few words about Tiffany, who is the IEEE Magnetic Society Distinguished Lecturer for the year 2022, which is very prestigious. A few years ago, it was Professor Mtjs, who is also on board, and he gave a series of lectures. And this time it is Tiffany's role to come forward and really introducing these very basic lectures on spins, beats, and flips, essentials for high-density magnetic random access memories. Before she starts her lecture, I'd like to just say a few words. So Tiffany Santos received her PhD degree from Material Science and Engineering from MIT in US. Her PhD thesis was on thin film magnetism and spin polarized tunneling in magnetic tunnel junctions under the supervision of Jagdish Mudera at the Francis Bitter Magnet Laboratory at MIT. As well, she has worked at several places. Currently, she is the Director of Non-Volatile Memory Materials Research in the Research Division of Western Digital Corporation in Santos, in California, where she leads a team working on materials for magnetic random access memory technology and other exploratory projects. She first joined the company in 2011, when it was previously known as Hitachi Global Storage Technologies, to work on research of granular iron platinum media for heat-assisted magnetic recording. Prior to working in industries, she was a distinguished postdoctoral fellow and later an assistant scientist at the Center for Nanoscale Magnet Materials at Argonne National Laboratory, where she studied emergent phenomena at the interface of complex oxide heterostructures. Tiffany has an active role in professional societies in the magnetism community. She is a 2022 Distinguished Lecturer of the IEEE Magnetic Society. She was the Program Co-Chair of the 2020 Intermag Conference, and she will be the General Chair of the 2025 Magnetism and Magnetic Materials, popularly known as M Conference in Palm Beach, Florida. In 2009, she was awarded the prestigious L. L'Oreal US Fellowship for Women in Science. So it's really our great pleasure to welcome Tiffany to this seminar. I just like to mention a word that during our lecture, we don't take any questions. At the end of the lecture, I would like to request Tiffany to stop sharing the screen for 30 seconds and request all the participants to switch on the camera so that we can take a group photo just for a collage for later purposes. And then we will have the question answer session. Okay? So with all this, I request you, Tiffany, to start your talk. Really looking forward to a lecture. The floor is all yours. Thank you so much.
Thank you very much for this kind invitation to speak at this very nice seminar series. I'm joining you. It's morning for me, 7:30 a.m. In California. And I'll just go ahead and get started. So I am a distinguished lecturer of the IEEE Magnetic Society. We are the leading organization for bringing together people that do research in magnetism. There are local chapters located around the globe, and we organize conferences, major conferences like the Intermag and the MMM, but also some workshops and summer schools. And we have this distinguished lecture program bringing together letting some experts in the field go around and tell folks about the exciting research that goes on in magnetism. So if you're not already a member, I encourage you to go to the website and have a look and consider joining to be part of this great community. So I am at Western Digital. The headquarters is in San Jose, California, and we are a data storage company. Our major products in mass production, there are two of them. One is the hard disk drive. It is a magnetic data storage device. And the other is a solid state drive based on NAND flash. But I won't be talking about those really today. What I'm excited to tell you about now is the cool research that we are doing in the research division of Western Digital on MRAM, magnetic random access memory. So in this talk, I'm going to start out by telling you about the history of magnetic tunnel junctions, MTJs. And this is a interesting, as very rich history, and I like to tell the story, but it's important because the magnetic tunnel junction is the main component in these major applications that I'm going to be talking about, hard disk drives and magnetic random access memory. Then I'll give an introduction into spin transfer torque MRAM, and I'll tell you about the work that we're doing at Western Digital, a couple studies here, toward advancing a high density spin transfer torque MRAM, and then I will conclude. So a great place to start telling the history of the magnetic tunnel junction is with Ivar Gaver. He was in New York working for General Electric as a mechanical engineer in the late 1950s, and he wanted to study conductance between metals. So he came up with the idea of using an aluminum electrode and then using its natural oxide at the surface, aluminum oxide, as a tunnel barrier. And then he had the idea of putting a lead counter electrode, it's a superconductor, and using this tunnel junction structure, he showed the energy gap in superconductors measured by electron tunneling coming from the aluminum. So this was a remarkable verification of the BCS theory, and for this, he received the Physics Nobel Prize in 1973. A little while after Ivar Gaver's work, in the Francis Bitter Magnet Laboratory at MIT, there was Paul Tedrow and Bob Meservey. They were also using aluminum electrodes and aluminum oxide tunnel barriers, but this time the aluminum was the superconductor. And they had the idea of using a ferromagnetic nickel counter electrode. And with this tunnel junction, they showed the asymmetry of the spin density of states from the ferromagnet tunneling into the superconductor. This was the first experiment showing that spin is conserved in the tunneling process. And that's something that we take for granted now, as tunnel junctions are so prevalent in applications. But really, this was the first experiment to demonstrate that, and it broke open the field of spin polarized tunneling. And then a few years later, in 1975, Michel Julier in France, he was a graduate student at the time, and he was inspired by the work of Meservey and Tedrow. He had learned from them that spin is conserved in the tunneling process, and so he proposed tunneling between two ferromagnets across this insulating tunnel barrier. This was the structure that he used. The ferromagnetic electrodes were cobalt and iron, and with a thin tunnel barrier in between. Tunnel barriers are typically 1 to 2 nanometers in thickness. And he proposed a model, this model for tunneling between the two ferromagnets, saying that there should be two stable resistance states. So I will describe how this works. So in ferromagnets, what's special about them is that due to the exchange interaction, you have asymmetry of the density of states. You have a majority of one spin orientation compared to the other. So when the two ferromagnetic electrodes have their magnetization oriented parallel to each other, you have a lot of spin up electrons in one electrode and a lot of empty spin up states in the other ferromagnet, and this results in a high tunnel current and correspondingly a low resistance state. When the two ferromagnets have their magnetization oriented anti-parallel to each other, there's a mismatch of the density of states of the two ferromagnets, and this results in a low tunnel current and correspondingly a high resistance state. And the tunnel magnetoresistance ratio is the difference between the anti-parallel resistance and the parallel resistance over the parallel resistance state. Okay. So Michael Julier made this tunnel junction for his thesis work. This is the title page of his thesis here. And he did show tunnel magnetoresistance of 14%, but this was limited to just low temperature. By the time you got to room temperature, there was no TMR effect there. And there was no TMR observed at room temperature until 20 years later. So this was shown and published in 1995 by this team here at MIT. The principal investigator was Jagadish Mudera, but working with him at the time was Lisa Kinder. She is a high school student at the time. This was her very ambitious 8-week summer project assigned to her. In addition, a co-author was Terilyn Wong, a freshman undergraduate student at MIT, and then also Bob Meservey, who was retired at the time. So it's a great example of these scientists of all stages of their career coming together and making this important discovery of room temperature TMR for the first time. Now, also around this time, Professor Miyazaki and Tezuka, they observed TMR at room temperature as well. And it was this discovery alone that led to the major applications that use magnetic tunnel junctions, hard disk drives and MRAM. And I'll get to that in a moment. But there are a couple more milestones for magnetic tunnel junctions that I want to get to first. Okay. So in 2001, there was a first principles calculation saying that if you use magnesium oxide tunnel barriers with iron electrodes, the top and bottom here, and you have this specific crystallographic orientation for your barrier and electrodes, then you'll get a special situation where you have fully spin polarized electrons in the iron tunneling across the barrier, and in the MgO, they will give a lower barrier height, making it easier to tunnel for these fully spin polarized electrons. So this particular material set can give you a TMR of over 1,000%. And surely just a few years later, it was confirmed experimentally very high TMR from magnesium oxide tunnel barriers with iron electrodes. And this was shown and published in the same journal edition of Nature Materials from Shinji Yuasa, showing TMR 180%, and Stuart Parkin showing 220% TMR for MgO barriers. And over time, there's been improvements to the structure and TMR has increased. And now today we can see over 600% at room temperature for MgO barriers. This is a lot higher than what you can see with amorphous aluminum oxide tunnel barriers, which reaches around 80%, certainly staying below 100%. Okay. And that brings me to the applications for hard drives. So magnetic tunnel junctions were first used as the read head in hard disk drives introduced by Seagate in 2004. I believe that they were using titanium oxide tunnel barriers in the read heads at this time. And also toggle magnetic random access memory, first introduced by Freescale, now known as Everspin, in 2006. Okay, so I'll say a few more words about those applications of magnetic tunnel junctions. And we are all using magnetic tunnel junctions pretty much on a daily basis. A great example of that is that this This Zoom call is being recorded. It's streaming to a hard disk drive in a data center in some remote location. And then if somebody wants to view it later, it's a magnetic tunnel junction that will read back the bits making up this video and bring it to the viewer. Okay. And here's how that process works. So I'll tell you a little bit about how the magnetic tunnel junction functions inside the hard disk drive. So here we have the inside of the hard disk drive, where this is the spinning disk here where the bits of data are stored on a magnetic film that coat the surface. If you take a powerful microscope and look at this film on the disk, you'll find that it's made up of lots of magnetic nanoparticles. Groups of them come together to form a bit, and that's shown schematically here in the red and purple colors for bits, zeros and ones, lined up here in a track in the film. And at the end of this arm here is the head of the hard drive. And this arm can sweep back and forth and access so that the head can access any part of the disk. So the head is made up of the writer here that write the bits onto the media, and also the reading head here, which contains the magnetic tunnel junction sensor. So here we have a schematic of, first I'll describe what the tunnel junction is trying to sense. So the bits on the media here, they're shown as have perpendicular magnetization up and down. There are stray fields coming out and going back in to the bits depending on their magnetization. And this is what the magnetic tunnel junction will sense as the head flies over the surface of the media. And that's shown schematically here. We have the up and down orientation in the orange and the black colors here in the plane of the slide. And this is the magnetic tunnel junction here, with the white layers is the tunnel barrier, the free layer on the top, and a pinned reference layer on the bottom, and the current passes perpendicularly through the layers. The free layer can cant its magnetization as it senses the stray fields coming from the bits, and that corresponds to the resistance change here. The actual data on this transfer curve is the red curve, higher resistance state or lower resistance state, depending on how the free layer is oriented relative to the reference layer. So this is how the magnetic tunnel junction reads the bits of data in the media. The other major application that I'll focus more on from this point on is magnetic random access memory. And the first generation of products was Toggle Mram. It's still in production today. And Toggle Mram is an array of magnetic tunnel junctions. You have word lines and bit lines, and at every intersection is a tunnel junction storing a bit of data in the parallel or anti-parallel state of the free layer relative to the reference layer here. And you flip the magnetization of the free layer by a local magnetic field. The magnetic field comes by passing a current through the word lines and bit lines high enough to generate the field to switch the magnetization of the free layer. Okay. And these use aluminum oxide tunnel barriers. Okay, so at this point on, I will now describe spin transfer torque MRAM. Now, as I showed you in Toggle MRAM, there's a magnetic field generated by current pulses in the bit lines and word lines, and that's what writes the magnetization of the free layer in each Mtj. So this type of writing scheme does not scale well to small dimensions. But in spin transfer torque MRAM, you have this magnetic tunnel junction here, and it's a transistor that passes a current and writes by spin transfer torque. This type of writing scheme does scale well to small dimensions, and you can see that easily here in this comparison in this top-down SEM image, comparing the area occupied by 16 perpendicular magnetic tunnel junction bits. These have about a 60 nanometer diameter. And these fit into the area of just one toggle Mram bit. And so it's easy to see here that it's spin transfer torque Mram that will move us forward to a more high density memory. And indeed, there are already MRAM products available now. These are embedded MRAM products. They are used now to replace embedded flash because MRAM scales better to the 22 nanometer semiconductor technology node compared to flash. And so these major companies are partnering with these major foundries to make embedded MRAM products. So what is a spin transfer torque MRAM cell? It's this one magnetic tunnel junction that is your storage element and one transistor. The transistor supplies the right current to switch the free layer magnetization to be parallel or anti-parallel to the reference layer. And there's no magnetic field required here. So it's a magnetic device that does not need a magnetic field. And the writing happens by spin transfer torque. So I'll describe that. This is your 3 layers of the tunnel junction and a current passing through perpendicularly through the layers. So by conservation of angular momentum, the free layer feels a torque acting upon it by the polarized spins coming from the reference layer. And if that current is high enough, then the torque will be large enough to switch the magnetization. So showing here the Landau-Lifshitz-Gilbert equation that describes the precessional motion of the moment around an effective field. The Slonczewski terms here, this green and orange terms, they are added when a current is passed. So I just want to point out here that the spin transfer torque here, the one that's acting to flip the magnetization, it's directly opposed by the damping torque that wants to pull the magnetization back towards the field into equilibrium state. For this reason, for the free layer material, we want to minimize the damping parameter alpha as much as possible so that the spin transfer torque can be most efficient in flipping the magnetization. Okay, so spin transfer torque was discovered in 1996 by 2 theoreticians, John Slonczewski and Luc Berger. Okay. And so this is kind of a demo of the writing and reading of the magnetic tunnel junction in the STT MRAM cell. I'm showing here resistance versus voltage. We can start here at low bias and in the high resistance state, which is anti-parallel alignment of the 2 ferromagnets, or for example, a written bit of 1. And for when a bias is, when a voltage is applied to write from the anti-parallel to the parallel state, you have the voltage surpassing the critical voltage needed for switching, and we get to the parallel state or the low resistance state, for example, a written bit of 0. And then when you want to flip back back to the anti-parallel state, you apply a voltage in the opposite polarity to flip back to the high resistance state. So if you take the same tunnel junction and flip it by a magnetic field, this is what the transfer curve would look like. Okay, and this flipping of the free layer or the reversal can happen in a couple different ways. If the tunnel junction size is very small, for example, a diameter of 25 nanometers or less, then the flipping will happen by coherent rotation. So shown in these colors here, you start with all the spins pointed up and they rotate together as a single domain during flipping, and then facing downward with the magnetization in color blue. Okay. Now, if the domain, if the free layer size or your bit size is larger than 25 nanometers, the flipping will happen by domain wall nucleation and propagation. And you can see this in this on the right side here, I'm showing a micromagnetic modeling study of these reversal mechanisms. And so this one shows domain wall motion for reversal of larger bits. Here you can see that it's nucleated in the center, and the domain wall propagates outwards to be completely flipped. And you can see that that process, domain wall motion, it takes longer compared to coherent rotation. And especially it takes longer if the exchange stiffness of your free layer material is small. So you can see here that we will get faster switching by using small devices that are in this coherent rotation regime. And this is what would be needed for a fast and high density memory. Okay, so at this point, I want to tell you a couple materials tricks that have enabled perpendicular spin transfer torque MRAM. My role in the team is to deposit by sputtering the film stack of magnetic tunnel junctions. And so these are tricks that we're really using day in and day out, and that have enabled this technology. So one is, how do you get an epitaxial cobalt iron MgO interface that's needed for high TMR? How do you get that high quality interface in a manufacturable process? So this trick here was found and published in Applied Physics Letters in 2005. And you start out by sputter depositing cobalt iron, but in an amorphous state. And you get amorphous structure by alloying in boron, like 20 to 30% boron here. Then you deposit the MgO tunnel barrier. And fortunately for us, when MgO is deposited on an amorphous surface, it wants to take the desired texture, the 001 crystal orientation here. Then you put the top electrode, again, amorphous layer of cobalt iron boron. Then you can sputter deposit this at room temperature and then do a post-anneal step. During the post-anneal, the boron atoms diffuse away, diffuse out, allowing the cobalt and iron atoms to take on the texture of the MgO. And this is called a solid phase epitaxy. And you end up with coherent interfaces at the top and bottom of MgO with the cobalt iron electrodes. And this is how you achieve the high TMR. So this is used for both reed head magnetic tunnel junctions and spin transfer torque MRAM products. Okay. The other trick is, how do you get cobalt iron with perpendicular magnetization? Because cobalt iron in the bulk form, it really wants to be in plane, and it is used with in plane orientation for reed heads. But for spin transfer torque MRAM, we want perpendicular magnetization because that will lead toward a low switching current and a high density memory. And the way that you get perpendicular magnetization is by thinning down the thickness of the cobalt iron layers here. So it was found, this trick was found independently by these two groups here in 2009. And it's understood that an interfacial perpendicular magnetic anisotropy arises from orbital hybridization between the iron and the oxygen. And this gives rise to an interfacial perpendicular magnetic anisotropy that dominates over the bulk in plane one. And in fact, now conventional free layer structures use an MgO capping layer on top, and then you also have this MgO layer at the bottom. So then you've got these two interfaces generating the interfacial PMA to further enhance the effect. Okay, so let me review some important concepts of spin transfer torque Mram. For the writing, I showed you that this is due to spin transfer torque, and that's characterized by a critical switching current density JC0. And you can see here that this largely depends on materials parameters of the free layer: saturation, magnetization, anisotropy field, the damping parameter, and the thickness. And for this reason, this is something that the materials team that I lead, we spend a lot of time tailoring these properties here for best performance. The reading operation is done by tunnel magnetoresistance effect. The retention, so this is how long can the free layer retain the magnetization of the written state, either up or down, before you get a thermally activated reversal, and then your memory would be lost. So the retention comes from the perpendicular magnetic anisotropy energy, and that's characterized by the thermal stability factor delta here. And retention for products is typically reported as a unit of time, for example, a number of hours or years before you get a thermally activated reversal. Endurance is the number of write cycles reached before a specified failure rate. For example, a failure rate of 10 parts per million. So how many times can you pass a high current through the MgO tunnel barrier before you get a failure? And typically a failure is a breakdown of the barrier to a short. Okay. And different MRAM products will require a different set of specifications. For example, embedded flash products that are available now, they typically have magnetic tunnel junction diameter sizes 40 nanometers and above. Retention, typically the spec for that is 10 years at an elevated operating temperature, write currents above 100 microamps, TMR values above 100%, and endurance about 1 million cycles. But if we want to push and advance this memory toward to be more high density, for example, a standalone DRAM replacement, then we're going to need very small magnetic tunnel junction sizes to get that high density. So the goal is 20 nanometers or less, a write current less than 20 microamps, TMR values very high, approaching 300%, and endurance 10 to the 12 cycles, kind of reaching more towards that unlimited endurance. And the reason why we would want such a high performance memory is because we live in an era of big data applications that have massive storage and performance requirements. Applications such as all of our devices being connected on the Internet of Things, big data analytics touching all sectors of our economy, for example, retail and healthcare and finance, and then applications like self-driving cars that require real-time processing of visual data. So these types of applications, they require an effective memory hierarchy that is fast and low power, and they generate a need to bring high performance memory closer to the computing units. And this motivates our research into new physical mechanisms like spin transfer torque that can store the information for these applications better than the memories that we have available now. Okay, so at this point, I will discuss the challenges toward achieving a high density STT-MRAM and a couple projects that we're working on Western Digital to address these challenges. Okay, so the challenges for scaling to smaller cell sizes, 20 nanometers or less, is that you already, by making smaller bits, you lose thermal stability because of this loss of volume V. So to compensate for the loss of thermal stability due to small cell sizes, you need to increase the perpendicular magnetic anisotropy, but at the same time, keep your switching current density low. So you want to keep the switching current low because very high currents will cause breakdown of your MgO barrier, but also In a high density memory, you're gonna have a high density of transistors. They're gonna be very small, and small transistors can only supply very small current, but yet that current needs to be large enough to switch your MRAM. Okay. Another major challenge is on the fabrication side. How do you etch MRAM bits at tight pitch that's needed for a high density? And how do you do that while maintaining tight distributions of your various performance parameters? Okay. Another challenge is if you make lots of small bits, your distributions is going to go up for these small cell sizes, and you need to compensate for that by boosting your read signal. So then TMR needs to be upward toward 300%. Okay. So the first one I want to address here is this very challenging trade-off for anybody working on MRAM. This trade-off between thermal stability and low switching current. Now, if we want to increase thermal stability by increasing MS and HK, that also is going to increase your switching current. For that reason, the damping parameter here becomes key. And one way that we have worked to address this in our research at Western Digital is to engineer free layers that have low switching current. And I'll give an example of that here now. So conventional free layers, they have a thickness over 20 angstroms. So the free layer structure is mainly cobalt iron boron, and it's shown here on top of the MgO tunnel barrier and with an MgO cap on the top. And inserted somewhere in the middle is a heavy non-magnetic metal, tungsten in our case here. The tungsten is needed to act as a place for the boron atoms to go during the post-anneal process. You want the boron atoms to diffuse to this tungsten layer rather than be anywhere close to your cobalt iron MgO interface that's needed for high TMR. So that's otherwise the tungsten there acts to reduce the saturation magnetization and increase the damping parameters. So we want to minimize as much as possible how much tungsten we put in there as the boron sink. So our strategy for doing this is just to overall reduce the thickness of the free layer. That allows us to reduce the tungsten spacer thickness substantially, but yet still maintain perpendicular magnetic anisotropy. So for example, here, the free layer thickness is reduced down to 12 angstroms. And we found that the properties improve even more if we take this single tungsten spacer and split it into then two even thinner spacers here, yet maintaining the same total 12 angstrom thickness. So I'm showing here a TEM cross-section of, for example, a 13 angstrom cobalt iron boron free layer with the MgO barrier at the bottom and the MgO cap at the top. So we proceeded to do this free layer design for a ladder of free layer thicknesses. So 17 angstroms was the thickest one, then 13 angstroms down to 12 angstroms. And by reducing the free layer thickness, we're able to substantially reduce the tungsten spacer thickness. And so this resulted in a lot higher saturation magnetization, a reduction in the damping parameter, and also an increase in the exchange stiffness, reaching values that we know for bulk iron, even for these cobalt iron boron free layers that are very thin. We proceeded to make bottom pinned MRAM devices using these free layers. And these devices were made by optical lithography. They have diameters in the range of 55 to 130 nanometers. And we saw TMR values in the range of 100 to 125% for these devices. And healthy coercivities for switching of the free layer approaching 2.6 kilo oersteds for the smallest devices. Okay. And what we wanted to measure from our devices is the thermal stability factor and the switching current density. So here's the results for the thermal stability factor. It was determined from field switching probability measurements where those results were fit to a domain wall reversal model, because for these sizes of devices, we're in the domain wall reversal regime. Okay. And this analysis gives the domain wall width, the domain wall energy density, and the thermal stability factor found by taking the domain wall energy density multiplying by diameter, free layer thickness over KBT. Okay. And we found that it is the thinner free layers with the better magnetic properties that give a lot higher domain wall energy density, and therefore they are able to maintain high thermal stability even though the free layers are quite thin. Then the critical switching current density we found by fitting pulse width dependence of the critical voltage using a thermal activation model for spin transfer torque switching. We found that it's the thin free layers that have substantially lower switching current density by 30% compared to the 1.7 nanometer free layer, the thickest one of the latter. So then for the figure of merit, the spin transfer torque efficiency, which is defined as the thermal stability factor delta over the critical current, it's the thinnest free layers that have the highest efficiency because they have they maintain high thermal stability factor, yet at the same time having this low switching current density. Okay, and then the other experiment that I want to describe now, it addresses this fabrication challenge of etching Mram bits at tight pitch. And at Western Digital, we had the goal of making an Mram bit array at 50 nanometer full pitch and show that we have physically separated bits and that you can do an electrical test of bits and see the free layer switching. Now, in literature, there are lots of very nice examples of performance of Mram bits that are isolated. For example, here's a 10 or 11 nanometer bit from IBM and Samsung showing very good performance. However, there are very, very few papers addressing Mram bits at tight pitch. Okay, and the reason why this is so challenging is because you need to etch a lot of metal to make your Mram bits, because it's primarily a metallic multi-layer, and that metal gets redeposited on the sidewalls and will short the MgO tunnel barrier, and then you'll get no electrical data. For example, this study from Samsung, they did the tight pitch array, but with no electrical data. So the best demo that we know to date comes from SK Hynix and Toshiba, where they have a 90 nanometer full pitch demo at 4 gigabits with electrical data. However, if you want to be competitive with a DRAM density, you need to achieve at least 56 nanometer full pitch. So okay, so here's how we made our tight pitch Mram bit array in our research clean room. So we started out with a blanket film of a magnetic tunnel junction, and we put a hard mask on top for the patterning. The hard mask is made of tantalum nitride, diamond-like carbon, and chrome. And the hard mask was patterned by E-beam lithography and etched by reactive ion etching. And you can see that the hard mask then has this very high aspect ratio. This is the tilted SEM and the top-down SEM view of the hard mask. So very tall pillars of high aspect ratio hard mask with vertical sidewalls. So this is a good hard mask for then etching the Mram bits. And that is done by ion beam milling, first at a low angle to etch into the depth of the metallic multi-layer to form the bits, and then again a next step at high angle to mill away the redeposited material on the sidewalls and prevent electrical shunting. Okay. But then we want to be able to make contact to our bits, and we don't have easy access to expensive CMOS. So we do what we can in our research clean room, and we made bottom point contacts. Let me see here. Okay, starting out with metallic individual contacts patterned by E-beam, and then another E-beam step to make the arms out to the contact pads. Then we do a dielectric refill and a chemical mechanical polishing to make the surface very, very smooth for then the Mram stack deposition. Then the bits were patterned using the process that I described previously. We did a fill with a spin-on glass for planarization, and then put a common top electrode, so that schematically this is what the cross-section looks like, but then I can show you with real images here. So these are SEM images here on the left of the individual bottom point contacts, and then the contact leads. And then the tight pitch Mram bit array is fabricated on top of the contacts. And then if we take a diagonal slice right here, then we get the cross-section TEM images shown here. The top one is for a 52 nanometer full pitch array, and the lower one is for a 50 nanometer full pitch array. And you can see excellent E-beam alignment for individual Mtj pillars on top of the bottom point contacts. You can see physical separation of the bits with no sidewall redeposition, and good magnetic properties, because we do get the testing of individual bits showing TMR of 100%. So at this point, I want to conclude my talk. The message that I wanted to say in this lecture today is that we are all using magnetic tunnel junctions to store our data. And this has been the result of major discoveries and breakthroughs at the basic research level over decades, like the first experimental demonstration of spin polarized tunneling, and then much later, room temperature tunnel magnetoresistance for the first time, and so forth. And then advancements continued, such as the discovery of spin transfer torque, which allows us to switch without a magnetic field. So this has given rise to spin transfer torque Mram, and there are products of those available now. From this point, we need further innovation in materials and fabrication and memory architecture to enable a much higher density memory with cell sizes below 20 nanometers. So I would like to thank the IEEE Magnetic Society and these folks here that have inspired me to put this lecture together. So thank you very much for your attention.
Yeah, thank you, Tiffany, for this wonderful lecture. On behalf of everyone, I clap for you. A really excellent lecture. I am sure there would be a lot of discussions, but before that, yeah, thank you for stopping sharing. I request all of you to switch on your camera.
All right. Hello. It's great to see the faces, the audience.
Yes. Hello, Andreas.
Okay.
No.
Yeah. Okay. So a lot of people have not switched on the camera, but it would be nice to have you. Anyway, I take a screenshot now. Smile. Well, some people are still. Mtjs, we can see you. Mtjs is probably driving.
Some of the camera died.
Yeah, you need to position the camera correctly, Mtjs.
I tried, but somehow it doesn't want to switch it on.
We don't believe that.
You know, maybe I'm not good looking enough.
Oh, come on. Ask others. You don't know that. Okay, cheers. One more trial. Cheers. Okay, so thank you so much. I think we can now go back. You may kindly switch off your camera, and I request Tiffany to share the screen again.
Okay.
All right. I see already one question in the chat box by Chandra Murapaka. He's a faculty at Ieee Hyderabad. He said, wonderful talk, thank you. How do you eliminate shadowing effect while cleaning the sidewall deposition?
Yes, this is something that adds a challenge to the process for sure. Oh, here we go. Yes, so really for the hard mask, what is important to achieve is this high aspect ratio with the vertical sidewalls. And then the milling process is this two-step process where the second step focuses on milling away the redeposited material on the sidewalls. In all of these etch steps, the substrate is rotating to get a uniform removal of material on all sides. So it's very close attention to the profile of the hard mask, and then figuring out how to tune this angle, and then and also for the pitch that you're trying to achieve.
Okay, thank you. I think we can take the next question by Andreas Berger. Andreas, please unmute and ask.
Hi, Tiffany. Thank you for your very nice talk.
Oh, great. Thank you. Hi, thanks for attending.
My pleasure. I saw your other talk, I guess, with the Italian group the other time as well, but I didn't get to ask my questions there.
Oh, okay. So you've had some time to think about it.
No, not really. I was just curious. I thought the thickness, if I saw this correctly, for the tungsten that you're using was 0.15 angstrom. So this is 5% of a monolayer, right?
Mm-hmm. Yes.
And
yes.
I was wondering, of course, this is the, large area average there.
Mm-hmm.
But wouldn't
yes.
that be a big problem in scaling the technology? Because if you make it smaller and smaller, then the variability of how much tungsten you get in every device will vary very significantly in terms of its relative contribution. So I was wondering if you could comment on that. So
that's an excellent point. So yes, these thicknesses, as you say, it's not feasible for a real physical thickness. So this type of thickness level does mean that you have dispersed in discontinuous monolayer of atoms to form this layer. And then already, so the sputter tools that we have and that are available for even production, they have excellent uniformity across the surface of the wafer. And then you can do things like really bringing down the sputter rate to have better control to hitting this desired thickness. But then, as you say, if you're really trying to push to small dimensions of your bits, and then you may run into this room where then you get variability of where these atoms are in relation to your bits. Right. So yeah, so then you have to think about perhaps designs that may not even need a tungsten layer or a spacer layer, or choose a different material other than tungsten that will still give you very good properties and won't limit you with this thickness problem. Yeah.
Mm-hmm. Okay, no, it sounds an interesting idea, and we try to make these very, very thin overcoats. And of course, but in more fundamental experiments that we do, we have then really the area to average. But if you try to make an array of small scale device, you really get beaten up, I think, at some point.
Yeah, and then it's the device to device variability that you start worrying about.
Yeah. If I might, I have a other question regarding the read process. Is temperature any impact, or is temperature impacted as you trying to read, to write the device? Are you actually increasing the temperature of the free layer? And how, if so, how do you monitor that?
Okay, so for Mram applications, we do have to plan for the operating temperature to be a lot higher than room temperature. So really the spec is specific for the application, but typically you have to know how your Mram performs at, say, 85 degrees C or 100 or 125. Okay, and so we also collect that information of performance at elevated temperature. Okay, you had asked about reading. Yeah, so at elevated temperature, the TMR value is going to go down, and it's also going to go down. There is this bias dependence, or TMR does vary with voltage and temperature. So elevated temperature, TMR value is going to be lower, and then also at higher bias, that you need for read, TMR value is going to be low as well, which is why which is why we have this goal of very high TMR values to get the best signal possible during operation. Yes. So so writing, how does temperature go into effect with writing? So at elevated temperature, coercivity goes down. It makes writing easier. Okay, so writing is easier. However, the hard one is making sure that you meet the retention spec at elevated temperature. Yeah. Yeah.
But actually, the writing process raises the temperature, or this is not?
Oh, okay. So you have elevated temperature just because of the environment of your chip is going to have elevated temperature. Let's say you have a automotive application or so. But then, yes, if you're asking about, passing high current through the magnetic tunnel junction, yes, it also causes a heating up, a joule heating. And we work to account for that as well. Yeah.
Okay. Thank you very much.
Yeah.
Actually, I have a similar question what Andreas asked. But already he has asked and you have clarified. I just wonder what happens when you put tungsten on cobalt, iron, boron, or in between, that the alpha value also decreases. In this slide, you show 0.004. It goes to 0.003, which is definitely better. So what happens?
Yeah.
Because when you put tungsten, there may be some spin pumping happening, and that should enhance rather the,
Yes,
alpha.
yes. So tungsten's heavy. Another popular one to use as a spacer material by other groups is tantalum. These introduce spin orbit. They're going to raise the damping parameter. And it's certainly a general trend that we find that if we do a tungsten ladder beyond what is here, we will see a corresponding increase in the damping parameter for the thicker tungsten layers.
Okay, so it is basically the thickness of the free layer. And when you reduce it, your alpha is also subsequently reduces, isn't it?
It's a lot has to do with saturation magnetization.
Okay.
Yeah.
All right. There are two more questions in the chat box. I will read it. By Suryakant Mondal. He said, at the beginning of Mtj, they used superconductor. So the measurement was done at low temperature or room temperature?
Definitely low temperature. Yeah, so thanks for your interest in that question. This was really the way of doing spin polarized tunneling and measuring polarization, was using a superconductor as the spin detector. And for the experiments like from Messervy and Tedrow in the 70s and onwards, they were using this very thin aluminum film, and the measurements were done typically around 400 millikelvin. So to get a robust superconducting state of the aluminum, and it could clearly show the asymmetry of the spins tunneling into it from whatever ferromagnet. By that team, there are a lot of ferromagnets studied using that method.
Okay, thank you. The next question is, you first showed that people initially used aluminum oxide, and now you are using tantalum. So can you please tell a little more about the dependence of the special layer?
Mm-hmm. Yeah. Let's see here. Okay, so all of the initial work and even products now, they use amorphous barriers, and you can get good TMR values. Well, let's say probably not surpassing 100%, but you can get usable TMR values and make products from those, which is exactly what these early generation of products did. Okay. Now, in the case of the MGO tunnel barrier, this is a specific case. It's a very nice study led first by a theoretical prediction and then later shown experimentally of that it's kind of referred to as a spin filter, where you get this, you have this unique combination of MGO and an iron-based electrode that gives you tunneling of fully spin polarized electrons from the iron. Now, for example, if you do amorphous aluminum oxide and iron electrodes, I think on top and bottom, let's say at most you get a spin polarization of the iron at best 50%, and you'll never, so then you'll never reach several 100% TMR with that. Whereas with the MGO barrier, you can get nearly complete polarization of the iron in the tunneling process. So that would be P close to 100%.
Yeah, so basically telling that the MGO is now the best spacer for TMR, isn't it?
Yes, it does give you the higher TMR values. Now, folks can think of novel materials that will also lend itself to this spin filter effect. For example, some spinel barriers, there has been some nice demonstrations of high TMR with those as well. They are more challenging to make high quality, and especially in a manufacturable way. But there are other materials that can also lend itself to this filtering effect.
Yes, thank you. The next question is by Skylab. Stir field generated from each bead is strong enough to make difference in resistance in read head. Then what is the effect of such stir field on nearby or sidewise beats?
Oh, I'm sorry, the audio was breaking up and I didn't hear the question clearly. Oh, is it in the chat?
Okay, I'm sorry for that. Yes. So, am I audible now?
Yes.
Okay, the stir field generated from each bead is strong enough to make difference in resistance in the read head. Then what is the effect of such stir field on nearby or sidewise beats?
Okay. Then what is the, oh, yes. Okay. Yes. So, so far for the pitch that we're trying to achieve, stray field is not causing a problem of interaction of neighboring bits. The free layer is robust enough that it's not going to flip under the influence of any stray field coming from its neighbor. Yeah, so then also stray fields, the stray field can be tailored as well by kind of compensating the moments coming from the reference layer and hard layer underneath the tunnel barrier. And you can tune what stray field comes from there and what is felt by the free layer and the neighboring bits.
Okay, thank you. I see no more questions. So maybe you can stop sharing. Very nice. A lot of nice discussions. I like to share my screen now. Okay. Well, I recently updated my screen, my Mac operating system. Now I can't. Pushpendra, can you share your screen, whatever the memento? I'm sorry, I cannot share my screen. Strange.
Yes, sir. Just give me 30 seconds, sir. I'm free.
Yeah. Okay, maybe now it's. Sorry, strange. Just got updated in last 1-2 days, and I didn't realize that it needs additional permission. I have to do something. I need to quit Zoom. Anyway, so Pushpendra will do the needful. Thank you all for being patient. All right, here we go. Okay, Tiffany. So a small token of appreciation from our W2S team. I will read it for you. Webinar series on spintonics, National Institute of Science, Education and Research, NICER, Bhubaneswar, India, takes pleasure in presenting this plaque to Dr. Tiffany Santos from Western Digital San Jose in California, and who is also the IEEE Magnetic Society Distinguished Lecturer. In recognition and appreciation for being a valuable speaker to give a lecture on spins, bits, and flips, essentials for a high-density Mram. So thank you so much for this excellent talk. We really appreciate. Thank you very much.
Thank you.
And
Thank you. My pleasure.
Yes.
Okay.
And all of you, see you next week. And yes, you want to say something? Okay. All
I
right.
just pressed the wrong button. Bye-bye. Thanks for
Bye-bye. Bye-bye all. Have a nice day.
Bye-bye.
Bye all.
Bye.
See you.
Thank you.
Bye.
Bye-bye.